Hello, it's Brian again. I want to talk about part 3 in our retrieval system models investigation. Start off just with a little eye candy, some scenes I made at the Library of Congress. Lovely building, worth a trip there if you've never been there. But more to our point now, I want to talk proximity measures. It's a different way of comparing requests and documents. To review briefly, we looked in the past at retrieval rule. Here we're going to be thinking about criterion for matching index terms and search terms. We'll be looking at how how the search engine relates the status value to the request. We're going to consider the retrieval status value in a little different way. It's always been the case that the retrieval status value has given us the status of each document in the collection at the end of a search, and has always indicated the ranking of the document, but that ranking has generally been a binary ranking. It's retrieved or not retrieved, relevant, not relevant, yes, no. But now we want to talk about weighted systems, systems that predict the probability of satisfaction that a document will give to a user. In order to do that, we're going to start off with the very earliest of the systems, often called the overlap system or the coordination level system. There's a tiny system here, a tiny collection of 4 documents and 1 request. The index record, as has been the case in the past, is 1 or more descriptors. So for each of the documents here, there are several descriptors. Search request is 1 or more descriptors. The retrieval status value, instead of being yes or no, retrieved or not retrieved, is the set of all integers, all the counting numbers. The retrieval rule is apply to each document the number of terms that are in both the search request and the index record for that document. So let's take a little run through that. The request has B. Does document number 1, book number 1, have B? Yes, it does. So we add 1 to book 1. Does it have K? Yes, it does. So we add another to book 1. Does it have L? No. Q? No. No. Yes, so we add 1 more. No. So book 1 has a value of 3, an overlap of 3. If we go to book 2, we won't go through it step by step, but we can see it has, doesn't have BK, but it has L and it has W. That's all, so it has 2. Book, it has an overlap of 4 items. It has S, W, Q, sorry, I skipped Q, and Z, so for a total of 4. Book 4 has 4, but they're different, B, K, Q, and Z. So the recommended order here in probability of satisfaction to the user is book 3 and 4, which are tied, although they're different. The overlap number is the same. Then book 1, which has 3, and book 2, which is not totally irrelevant. It's not 0, but it is the least useful, predicted to be the least useful of all the documents in our collection. Later on, probabilistic searching became the thing. In Europe, Steve Robertson and Karen Spark-Jones worked on enhancing user input. What they did is let's let the user not only tell us what terms they're looking for, but how important those terms are. So a request might have three terms: risk, seismology, and building code. Most interested in risk, quite interested in seismology, and somewhat interested in building code. The things we're looking at here: index record, one or more descriptors; request record, one or more search terms, each with a weight; retrieval status value, set of all integers. The retrieval rule, a little more complicated, applied to each document the sum of the weights associated with the request descriptor terms that are found on the document. So let's run through that because it is a little complicated sounding. Fairly simple in practice, complicated sounding. In book one, request has building code and the book has building code. In the request, the user said, I'm weighting building code at a level of 3 on a scale, say, of 10. So we had 3. It doesn't have seismology, so 0, level of 3 on a scale, say, of 10. So we had 3. It doesn't have seismology, so 0 for seismology on book 1. It does have risk, and risk was rated highly, so we add that. And there's nothing about geology, so we have 3 plus 0 plus 8 plus 0 for a total of 11. In book 2, we go through the same process. We see seismology and building code for 6 plus 3, or a total of 9. Book 3 has seismology, and that's the only thing. And seismology is worth 6 points. And then book 4 has all 3 request terms for a total of 17 points. So weighted response would say, look first at document 4. It's rated pretty highly, 17 total. Book 1 would be your next best bet. Book 2, not too bad. And book 3, not awful, but the lowest on the list here. In California, Bill Marin and Bill Cooper had sort of the opposite thought, the bookend thought. Let's weight the descriptions in the documents, and that could either be by index or guess or evaluation, or by computer counting how many times a term occurred. It doesn't matter. The issue is that we're giving the description of the documents a good deal of weight, or giving them weights, I'm sorry. So similar to the other things, index record and search requests, one or more descriptors, except that the index record for each book has weights on the terms. Retrieval status value is all integers. The retrieval rule applies. Retrieval status value is all integers. The retrieval rule applied to each document the sum of the weights associated with the index descriptors found in the request. So sort of like what we just had, except we're going in the opposite direction. Book 1 has budget, and that's in the request. That's in the request. Book 1, that's in the request. As Trident, for Trident missiles, that's not in the request. So the value of 10. Let's go to where we have only the term Congress in common between the request and the document. Book 3 has budget and Pentagon. And book 4 has Defense, Reagan, Pentagon. So we have a weighted output to the user. Take a look at book 4. That's got a pretty high score. Take a look at book 1. That's got a high score. Book 3, not too bad, kind of close to book 1. Book 2, bottom of the barrel, but again, not totally irrelevant. In the early 1980s, a unification of the two models came about when Steve Robertson visited Berkeley and worked with Bill Marin and Bill Cooper, trying to put the two ideas together, the weighted request and the weighted index records. What they were doing was trying to come up with a way to measure the similarity between a document description and a request description. What we're going to do in the next few slides is take a look at a very simplified version of that model in its earliest stages. What they did was to try to picture this similarity measure as a graphical space, a geometric space, and they wanted to make documents points in that space and any request a point in that same space, and then somehow measure the distance between any request and each and every one of the documents in the space. So at the very simplest level, we're going to do this in 2 dimensions because that's all we have available to us on a monitor screen. What they did, what Robertson, Marin, and Cooper did, was to say, we're going to make a graph, and every search term, every vocabulary term in the system will be one axis on this graph, one dimension in the graph. So if you have 2 dimensions, you can have 2 terms. If you have 3 dimensions, you need, if you have 3 terms, you need 3 dimensions. If you have 1,000 terms, you need 1,000 dimensions. Getting much beyond 3 dimensions is hard for humans to visualize, so we're going to start with 2. All the same properties hold, whether it's 2-dimensional or 10,000 dimensional. Just more things to count once you get up above 2. So we're going to consider 2 vocabulary terms because we have only 2 dimensions, and those 2 terms are going to be art and science. Every document in the collection and every request that comes to the collection can only be posed in art and science, but we can give numbers to both. We can weight them as points on the graph, as coordinates on for each of the axes. Knowing a little geometry offers different ways of measuring the distances. Let's take a little look, a tiny fragment of a collection here. We have our 2 axes, art and science, and the first document that's in the collection is described as science, and it's pretty far out on the science dimension, on the science axis. So on a scale of 1 to 10, it has a value of 8. So we see it's moved over quite a ways to the right along the x-axis it would normally be. It's a little bit about art, so it's up 3 on the art axis. So it's over 8, up 3. The second book in the collection is still a lot about art, a lot about science. It's over 8, but it's really even more about art, so it's way up near the top on the art axis. So this document lies in this space at over 8 for science, up 9 for art. Then we have a request come in. This may be from somebody who is looking at artists who trained a little bit in science. So science is only over 2, but art is up 8. So now, if we look at this, we can almost say, oh, if I eyeball that, it really looks like the request is a little closer to document 2 than it is to document 1. Document 1 is that far away, document 2 is that far away. Document 2 arrow looks shorter. So I would guess that by measuring distances, I'm going to find out document 2 is closer than document 1. Now, if we have 1,000 documents and some of them are very close to each other, it might be harder to eyeball them. If we have 3 or 4 or 10 or 1,000 different axes trying to locate just by vision alone where the closest document is, becomes almost unimaginable. But there are ways to get around that. So here we go. To measure those distances, to measure that arrow from the request to document 1 and the arrow that's from the request to document 2, the first thing we're going to try to do is make each of those distances, request to document 1, request to document 2, the hypotenuse of a right triangle. This is something one usually learns in elementary or middle school. Hopefully it hasn't evaporated. The reason we're doing that is because the hypotenuse of a right triangle is easy to calculate if we know the length of the sides. So we're going to say the hypotenuse is the square root of the sum of the squares of the lengths of the other 2 sides. Sounds good, a good line if you're at a party. So let's step through that and just see how it works. We're going to get rid of some of the labels here, just make it a little clearer. So here we just have the request is over 2 and up 8. Document 1 is over 8 and up 3. Document 2 over 8 up 9. So I'm going to form the right triangle, or the distance from request to document 1. There's the right triangle. Side A, we can actually measure because we know some points on the graph here. We know that the end of that line, side A, is over 8. The right-hand end of it is over at 8 points on the graph. But we know it doesn't go all the way to 0. How far does it go? Oh, if we look at the request, we see that it's over 2. So the actual length of side A is 8 minus 2. The distance of D1 along the axis minus the distance of R along the other axis. So 8 minus 2 equals 6. To find side B, we can say, oh, the top of it is at 8. It's up 8 on the art, excuse me, on the art axis. And we know that the document 1 is up 3. So we're going to have 8 minus 3. Length of side B is the distance of R up the art axis minus the distance of D1 the art axis. So 8 minus 3 is 5. So we have sides A and B determined. A is 6, B is 5. We plug those into the formula for a hypotenuse, which is the square root of the length of side A plus squared plus B squared. So A squared is 6 squared, B squared is 5 squared. That's 36 plus 25. We need the square root of 36 plus 25. This is handy where the for the calculator on your phone or your computer. Square root of 61 is 7.81 approximately. So we know that the length of the line from the request to document 1 is 7.81. We can go through the same process with the distance from the request to document 2. And here we have A is just 1 and B is, side B is 6. The calculation of the hypotenuse is A squared plus B squared, 1 squared plus 6 squared. 1 squared is only 1, 6 squared is 36. So we need the square root of 37, which is 6.08 approximately. And so we were right. The arrow from the request to document 1 is in fact a little bit longer. Not a lot, but a little bit longer. That gives you an idea of the very beginnings of the probabilistic approach to indexing. The next time we'll add another dimension. We'll step off the two-dimensional monitor and we'll step into my garden with some toys and look at measuring in a similar way with more dimensions and with some different ways. Thank you. Hope to see your comments in the discussion section on part 3. We need to get into the area of vector space. For those of you who may have forgotten high school physics, a vector is a directed quantity. We'll show that in just a minute. Here we're going to use a vector to represent the distance of each document and of the request from a point of